Good afternoon, everyone.
Good afternoon. Hello.
Sorry, don't know what's happening now.
Antonio, you're in mute.
You can start, Antonio.
I'm in mute.
Yeah, I don't know what's happening now.
You can stop sharing and
Yeah.
or now start again.
Yeah, sorry. Here we go. So welcome everybody and good afternoon. Welcome to our online technology meeting on agriculture. Today is June 2023. So we are going to talk about different photonic technologies that can be used in agriculture and in this the field industry. We are going to talk about the spectroscopy technologies. We are going to have mid-infrared sensors as well, LED illumination, hyperspectral cameras. So I'm sure that we are going to touch a lot of interesting topics for everybody. So welcome, and I'm glad that you are here. Just a few words about EPIC, in case somebody doesn't know us. EPIC is the European Photonics Industry Consortium. We are an association of more than 800 companies that are related with photonics technologies, and our goal is to ensure the photonics business in Europe by connecting people, helping you, our members, to find new partners and new collaborations, and also helping the members to find new business opportunities and learn about new technologies and markets. These are some of the benefits that we offer to our members. We help with the technological requests in case somebody needs help to find a partner or another company that can supply certain components, so they need integrator. We can put in contact with the right people. There is also possibility to access to market reports that are quite expensive, but we offer for free to our members. As I mentioned, networking activities last this online technology meeting, also in-person events that I will mention later on, and other benefits also related with human resources and also to investments. This is the great team we have at EPIC that are working in all the activities we do from the technology point of view, from the marketing point of view, and also as events manager. So, well, thank you to everybody for helping the technology people to prepare all these fantastic meetings. And yes, also a few words about the European Union projects where we are involved. EPIC is normally in charge of dissemination and communication activities in different European Union projects. And you have here a summary of all of them. GEPIX is related with the photonic integrated circuits topics in induced phosphide. Fabulous is related with fabrication of micro-optical components with free forms. Then we have MedFab, a pilot line that is dedicated to help companies that want to create a medical device using photonic technologies. Then Photon Hub Europe, that is an innovation hub for any technology related with photonics. Multiple, that was a project to develop a cost-effective multimodal monitoring solution, and also Pulsate, that is related with helping companies to introduce laser-based advanced and additive manufacturing to improve some of the processes of some of the components. So I'm open to give you more information about any of these European Union projects in case you are interested. So feel free to contact me. And also a few words about next events. So keep an eye on our website. We will have a lot of in-person events after summer. One about photonics in defense in Kielce in Poland. Another one related with space in Paris in France. One that is perhaps interesting for some of you in Tristan about photonics for bio and life science applications. Also the Dutch Watch and IMEC in Glasgow, the industrial quantum photonics technology at Optica, that is quite interesting topic nowadays, and I guess most of you are somehow involved in there. Also laser application related with battery manufacturing in Stuttgart in Germany. Then the technology meeting on microelectronics and photonics, two sides on one coin in Munich. And we will finish the year with photonics for cancer pathology and surgery in Antwerp, and the Tech Watch at W3 Fair in Jena. So as I mentioned, keep an eye. We publish in our website the agenda and all the information about the topics we will cover in our meetings, so you are more than welcome to register or participate. And this is the companies that register for the meeting today. So it's a very interesting distribution for agri-food. It's good to have system integrators and end users that are working in this field. Also, of course, components, laser manufacturers, sensors manufacturers, optics and micro-optics. And it's good to have a lot of R&D people that mention that is a topic that is interesting nowadays, and we will probably grow in the future with the new technologies they develop. And it's good to have also investor companies that are interested in them. And this is the agenda for today. So we will start with Jens Peter Wold from DigiFoods. Then we have one slide presentation from Cesar Martinez from Smart Hubs. We will continue with Carsten Giebeler from Spectrolytic, Marcel Zevenbergen from IMEC. Then we will go with CSEM, I think it's Pedram instead of Sebastian Blanc. Then Tristan Athanaze from Piseo, Tobias Kreklow from HAIP Solutions, and Marc Juarez from Seoul Semiconductor. And as you can see, the topics that we will discuss today, they are quite diverse. Spectroscopy sensors, mid-infrared, that is very interesting. A lot of industrial applications, they are trying to get benefit of this region of the spectrum. Applications developed by IMEC. Also LED manufacturing, hyperspectral imaging, very interested as well. So we can proceed with the first presentation. So I would like to introduce you Jens Peter Wold, that is Senior Research Scientist at DigiFoods, and he's going to talk about the smart spectroscopy sensors contribute to an efficient and sustainable food industry. So Jens, the floor is yours.
Okay, thank you. Then I will share my screen. Just have to find just wait a minute. Suddenly I can't see in my presentation here. Just wait a minute. Typical. Okay, I'll just share the screen now.
Good.
Is this okay?
Perfect.
Yeah, sorry. First of all, thank you very much for inviting me to give a talk at this EPIC meeting. I've never been to any EPIC's meetings before, but I see that it's very interesting for us to be connected. I'm Jens Peter Wold. I'm a leader of a research center or a long-term project called DigiFoods, or Digital Food Quality. It's a so-called, well, it's a Norwegian Center for Research-Based Innovation, funded by the Norwegian Research Council and the industry. And our main aim or task is to measure and digitize the food quality. And I will show you more about how we are working. It is a research center of 23 different partners. And what we do and what we want to prove and also obtain is just to show that smart spectroscopic sensors contribute to an efficient and sustainable food industry. So as you know, I mean, why are we doing this? And the main reason is, of course, that there is an enormous variation in raw material quality in foods. So foods may look alike, but they are very different. Like potatoes vary in the dry matter, which means that they should, for instance, be processed differently or sorted to different products, or to also to different markets. And it's the same with, for instance, salmon fillets or crabs, as I've taken in here. Very important if they are full or empty, and it's impossible to judge this by manual inspection. So that means that we have to utilize all of this variation in the best possible way, both to obtain and make a sustainable food industry, where we can decrease food loss and use the qualities in the best possible way. And of course, this also leads to increased profitability in the food industry. And our mantra has been for many years that if you cannot measure, you cannot control. So that means that these sensors that we are talking about here today are extremely important to be able to control these food processes and also processes in the field. So here are some examples of sensors that this consortium has made and now working on now, and what we have made before. So 3 of these systems are based on hyperspectral imaging. The one here on chicken, for instance, measures maybe 4 fillets per second. We can measure, in this case, fat pigment in salmon fillets at the same speed, food content in crabs, where you can measure 2 crabs per second. In the last case here with potatoes, I will show you later, it's a new NIR system that can measure deep into the potatoes. Now, these systems are based on NIR spectroscopy and also hyperspectral analysis, but we are also working on IR sensors and Raman spectroscopy. So we are working on a broad range, and the main thing is to try to make these systems work in line or in process in some way. So the concept of the center might look like a kind of a hyped concept, but it's not hyped, it's reality. So what we see here is just a food value chain going from primary production and then through production of industrial production of the foods, and then the food goes out to the consumers. And in this process, we already use, of course, these sensors along the whole value chain. And with today's digital systems, we can also collect all of this information up in this digital cloud and use it actually to optimize the value chain. So the main thing is often that we focus on the industrial process, as you see in the middle here, where you can use a sensor to optimize the process, either by adjusting the process settings, or you can do some kind of sorting. But in the next example here, I will show you how this is working with these chickens. So in this case, every chicken fillet is measured, and we measure some important quality features here. So just 2 meters down here, there is a robot that is sorting all of these fillets into 3 different categories. And so that's the sorting in the process, but all of the information about all the flocks of birds is collected up here in the database, and it is then connected to the farmers, and they have then all kind of information about the quality of the different flocks, and this can be used together with the farmers to improve the production of the chicken. So this is just a nice example of how we can improve the process, get the most out of the food material, and at the same time actually improve the value chain. So this is a concept that we are working along. And I also want to say before I continue that the most important lab in this research center is the process lines of the food companies. Oops, I lost. Sorry, I lost the slide there. I wanted to show all the companies involved there. So, okay, in DigiFoods we are about 23 companies. We are 8 food companies, and we are about 8 companies working on sensors, and 3 of them are members of EPIC. We are also several companies within analytics and IT platforms, and then we are also companies or research institutes, and together we are doing all of this work together. And what I wanted to say is that the food companies are extremely important because they define what some of the main needs, and much of the work we are doing is being done in the process lines, because that's where the sensors has to work. And that is also where it's very interesting to collect data and to do analysis of all the processes. Then I will just go further on and see what is next. So here is one example of a sensor system that we are making. So we're using both ready-made systems to analyze processes and make them work in the processes, but we are also developing new systems. Like this is NIR system dedicated to, in this case, potatoes. And the main thing here is that, first of all, it's quick. So you see here it measures all the potatoes that passes under. So that's one thing. So it has the ability to measure a large part of the process or the volume, but it's also designed so that it measures at least 1 centimeter into the potato. So I mean, most NIR systems, they measure just at the surface, but there are so many complex products like agricultural products where you have to measure in depth to get any useful information. And here it's just shown that we are, just to illustrate again, that we are measuring in depth, and the deeper we measure, the better results we get, in this case for dry matter, and the better instrument and better tool this will be for the food industry. And in this case, we are looking into different measurement geometries to obtain the best results for potatoes. And since this is about field measurements, I can also mention that the same system is of interest for measuring sugar content in strawberries. So there are several initiatives around in the world, also in Norway, where they are developing robots that can pick strawberries, but also other kinds of fruits. And we are very concerned or very into quality measurements, and as I've written here, robots, they have to be able to sense the critical quality features, and of course the color of the berry is important, but if you can measure also the sugar content and how they actually taste, that's also very important. And we have made a sensor for this, which is right now a bit big. We are working on making it much smaller so that it can actually be used by a robot. And that has, of course, some very nice and interesting features that can be used in the field, both for picking, but also just for monitoring development of sugar, and also for harvest, making prognosis about harvesting, and of course picking the correct berries. So now I've just shown a few examples of what we're doing, and I don't think I have time for more, and I missed my partner slide. I'm sorry about that. But if you're interested in reading more about DigiFoods, you can look into digifoods.no, and you can also look at these annual reports and find more information about what we're doing. So that was my main slides. So thank you.
Thank you, Jens. I think in the website is the partners are also included, right? So we can say everybody to go there so they can check the companies involved. And we have now time for questions and answers. So I encourage you to switch on the camera, raise the hands, and make the question live to the audience. While you're thinking your question, let me share briefly my screen again, because we will have next year an in-person event about this topic, the photonics for precision agriculture, farming, monitoring, management, food processing, packaging, quality control, all the topics related with agriculture, and is going to be hosted by DigiFoods. So book in your calendars these dates, 24, 25 April 2024 in Norway, Oslo, because we will have a very nice event to discuss and also to talk with the DigiFoods group about all these technologies. And now I stop sharing and it's time for questions. I saw that, yeah, Lars, I saw your question already, but you can make it live.
Oh, okay, let's do it live. Well, thank you. Manti spreekt, Lars here. Well, what we see is that cloud is not embraced by process owners. And obviously, there are risks, including hacks. You don't want a factory being closed off because of a hack. How do you see this evolving?
Well, if you ask me about like these digital clouds, I'm not an expert in this. So we are working with companies that collect all of this information, and they use it in-house. So of course, then they have to protect these things if that is your main concern. But some of our partners are already collecting a lot of information, using it to improve their processes based on these rapid measurements. And I think this will evolve further on, because I see it as a great potential. So you see, there's so huge variations in the food materials. So by, for instance, collecting this information over the year, they will learn a lot about seasonal variations, and also how they can optimize processes according to that, for instance. So yeah, that's my view on that.
Yeah, it's obviously necessary to collect all this information, but isn't that something that's need to be done not through the internet?
It doesn't have to be done through the internet. Maybe on the contrary. So maybe it's a misunderstanding. When I talk about cloud, I don't think about the internet. I just talk about the data storage. But of course, you can share if you would like. Are we talking about the same thing?
I think so. It's indeed not a cloud, but local systems, and this is exactly what I see as well. I'm embracing a transparent food chain, but the risk of process owners connecting their infrastructure to the internet, they're going to do that. So this is how I see this evolving as well. It's local system.
No, I see what you mean. So mainly these things are closed systems so far, and then let's say if parts of that information, if they can get some kind of services or so by sharing it, they can do so. But for us at this point, most of the information they are gathering with, let's say, the systems that we are developing and testing with them, it's just used in-house to optimize. We have quite strict rules, of course, of how we can use the data. And they also, like this chicken producer here, they probably also have strict data on how they on how they can use data from the farmers and so on. But I agree that data sharing can be a challenge in the future. So the main thing for us is that these sensors can at least collect all this information that is needed, whether it should be used in-house or shared by also other partners or other partners in the value chain.
Okay.
So thank you. Thank you, Jens and Lars. Marc?
So I have a question about what kind of a power device we are talking about. So the emitters that you use there, what kind of power they have, and what is the wavelength they also have? Is always fixed, or you have also different wavelengths for different?
Yeah, no, I can go in a lot of detail in this if you would like. So the systems that I showed you now, they were all based on NIR spectroscopy, and most of them work in this short NIR region where you are able to penetrate quite deeply into tissues. So it's in the region from typically 750 to 1050 nanometers. And they don't have very high resolution, because you don't need high resolution there to measure, for instance, water, protein, fat, temperature, these things. Some of the systems are also working up towards maybe around 1650 nanometers. But many of the systems that I showed you now, they are measuring in depth. For instance, to be able to measure through a crab shell, you need to be able to penetrate and measure at least to a depth of 10 millimeters. And that's why this spectral region is very useful.
Okay, and what kind of technology you use? It's an LEDs of Excel, or what? Do you know what kind of semiconductor you use there?
It's these are mainly the CCDs on some of them, if that's what you mean, yeah. And then one is ingots detector on one system that measures up to about 1260. So those are the main detectors in the systems that I've shown now.
Okay, thank you.
I can perhaps put you in contact, Marc, so you discuss also about illumination later on.
Yeah.
Yeah, so the illumination here is also on many of the systems. Actually, all of the systems are shown are based on interactance, meaning that you are illuminating on one area and you're measuring the light that comes up in another area, meaning that you are measuring in depth or at least to some depth. And I showed on the potatoes that we are doing work also to test different interactance distances, because it affects how deep you are measuring, and of course also the intensity of your signals.
Good. Let's move to the next question. Christine from Nortec Market.
Hello, thank you. Yes, I have a question. Those measurement systems you were showing for measuring sugar, strawberries, and potatoes and chicken, what is the status of those systems? Are these first prototypes where you do field trials, or is this already available as a serious system?
Yeah, no, they're both actually. So the systems that I showed on chicken, that is a system made by Tomra Sorting Solution that we were part of developing, and it is 100% commercially available. And the system on the salmon, also imaging, is made by a Norwegian company called Moderator. It is also commercially available. It contains cameras from Neo or HiSpecs, also a Norwegian manufacturer of hyperspectral cameras. So those are the first slide I showed with those systems. They are commercially available. And the last things on strawberries, they are under development. So they are part of our things we are working on now in the research center, both potatoes and also the strawberries.
Okay, thank you very much.
And Ian, last question. Ian from Vortex.
Okay, thanks very much for the presentation. It's quite interesting. Question then, what specifically are you measuring with the sensors? I mean, you've mentioned a couple of things there as you're answering the other questions there, things like moisture, fat, protein. Are there also any other things that you would currently like to measure that perhaps you can't measure at the moment?
There are many things that we would like to measure that we can't measure. But
give me an example.
An example. Oh, it's all about a lot of the food industry would like to be able to measure contamination and bacteria and things like that. Extremely difficult. So I'm not working on it because it's too difficult, or you need extremely high sensitivity. Right. Some things you could maybe address by using SIRS, like surface enhanced Raman spectroscopy. We are looking a bit into that.
Okay.
So, but with NIR, it's I would say within foods, then it's difficult to measure components or concentrations that are much below half a percent. But with Raman spectroscopy, we are doing work on fatty acid composition, which is of interest by quite many in the food industry. It's better than NIR in that aspect, I think. But if you ask me about things we can't measure, well, it's a lot. I can make you a long list. Like
okay,
yeah.
Maybe I'll drop you an email offline, because I can see that Antonio wants to move on.
Yeah. Okay.
Okay. Thanks for the answer, though. Appreciate that.
Send a mail. Yeah.
It will be great, Ian, if you can continue the discussion later on, so we can connect you both. Yeah. And it's time to. Well, we also have a question in YouTube from Luigi asking for wavelengths as well, but Jens, you already answered with all the information, so I think it's done. So we can move to our next speaker. We will have one slide presentation by César Martinez from Smart Hubs. So César, show us.
Good afternoon, everyone. Thanks to EPIC for the opportunity. Smart Hubs is a Spanish company, and we are specialized in the development of hubs. That stands for high altitude pseudo satellites. These are autonomous vehicles powered by solar energy and electrical engines. They operate from the low layers of the stratospheric, around 20 kilometers high, to cover the areas of interest in a continuous way, because they are operating during several months. So the important advantage is that the persistent operation, if you compare with the drones or even with the satellites, we have a very high spatial resolution, real-time information, thanks to the link with the ground control station. And one of the important advantages is also that this kind of vehicles could be recovered for maintenance and upgrade activities. So in fact, what we are doing is develop platform to integrate sensor for remote sensing. So, but this is a very complex project, and we are now working with an intermediate solution based in the use of tethered beams. We are talking about beams around 6 meters long, with a typical altitude up to 300 meters. We can lift payloads up to 10 kilos. The continuous flight time is something around 10 hours. Right now we are working with gyrostabilized optical camera. But this is quite interesting for agricultural application, but not only for agriculture. So at this moment, we are looking for developers of small payloads for agriculture surveillance, and also quite important for us for oil spill detection, and also fire detection and fire monitoring. So if you are developers of this kind of small pilots, please contact me and we can have some conversation with this project. So thank you very much.
Thank you very much, César. I don't know if there is any question in the room. I have a question. You mentioned about this gyrostabilized camera, but did you perform any test with hyperspectral camera or any kind of other spectrometer?
Not yet. We performed some demonstration and also some application for some customers with the optical camera. But that's the point we are right now. We like to integrate new kind of sensor to demonstrate the capabilities of the platform.
Very good. So, well, if there is no questions, I encourage you to take note of the email from Cesar. Perhaps you can put it also in the chat, your email address, and anybody interested can contact you directly to well, work in this new development. Well, I wish you the best for the future because it's a very nice. I also encourage everybody to visit your website because you have a very nice videos and pictures. So please go there and check what they are doing.
Thank you. Bye-bye.
And thank you again.
Right.
And let's go with our next speaker. Is Carsten Giebeler, is Managing Director of Spectrolytic, and he's going to present the mid-infrared sensor platform for agriculture applications. So Carsten, the floor is yours.
Right, can you see?
Yeah, perfect.
Okay, yeah, thanks for inviting me. I'm going to talk a bit about our mid-infrared sensor platform. So, okay, sorry. So spectrolytic, a little bit about spectrolytic. So we have two parts. One center is in Germany, where we do all the production and hardware development, a bit of it. And the rest is here in Scotland, in Edinburgh. That's where I am. So, and we are fully operational since 2016, and we are sort of, we grow organically. So everything takes a little bit longer, but we don't have any investors. So we are probably more known to people for oil inspection. So we work closely with Exxon and all other oil companies, but this is just to show that the platform that we have is really proven and it really works in harsh environments. This is a photo here of a steel application. We have these things on gas engine, in vehicles. So everything that we do is robust. And when I talk about mid-infrared, just so that everybody knows, we are talking from regions that we are addressing. So when we set out with spectrolytic, we really try to address this problem here. You always have a sampling point, then you need somebody to take a sample, you ship it to the lab, and depending where you are in this world, it takes ages to get a report back. And our aim was really to optimize all this by producing portable solutions or inline solutions to speed this up and to make data available to the customers in more or less real time. So, and how do we do this? We use mid-infrared spectroscopy, and mid-infrared spectroscopy is really one of the key analytical tools that people use in the laboratory. It's just a problem with laboratory-based systems is they're quite sensitive. You know, they have moving parts, they have lasers in there, and if it gets too hot or too cold or they vibrate, it all doesn't really work. So they're great for labs, but they are not at all suitable to take them out into the field. And this is sort of where we came in. We basically developed a process where we shrink everything down and still use the same wavelength range. And where this helps us is we can now use historic analysis that the customers have done in the lab. And we can use this data to basically develop the calibration files for the different applications. So why are we focusing on mid-infrared? You know, the speaker before was using near-infrared. The advantage of mid-infrared is that you look at the fundamental absorption, so the mask becomes a lot easier, and the amount of reference samples that you need in order to build your calibration file is probably a factor of 100 less. So considering for each reference analysis that you do, you have to pay a lab to do it, and it's a big, they cost 50, 60, 70 euros, whatever you do. So it's a big difference whether you need 20 or you need 2,000 of these things. And this is sort of where we see mid-infrared as quite a powerful tool because it makes it simpler, especially for applications where you have to constantly maintain the calibration files. So we've developed quite a few different products, but here's just an example of it. So on the left-hand side, you see our inline sensors. So in the middle is a portable one, and on the right-hand side is the Griffin. The right-hand side is a full spectrometer. It's actually camera-based. It gives you spectral and spatial resolution at the same time. All systems have no moving parts, and so a little bit answering the question that came about before. So the system can either be, they have embedded predictors on there, so all the calibration files can be loaded directly onto the system, so that the data can be sent via Modbus, via CanOpen, via serial interface directly to a PLC of the customer, if they want it, and then they can do with the data whatever they want. Or you can connect them up to, usually via LTE, especially this is mainly done because of data security, because then you have it completely separated from the customer's IT infrastructure. So LTE stands for mobile phone data. So both options are possible. So you can either have the data and send it directly to a controller in a factory, or you can send the data via LTE to a cloud, or you can do both, whatever you want, whatever the customer really fancies. So now I'm just going to go through some applications where we are active in. So just to explain, as for all these agricultural applications, we always look for partners. So we are no experts in agriculture, but we are very good at making sensors that work. So we are always looking for partners or projects where there is at least one end user there who has market access. Yeah. So here in this application, the customer was interested in measure the humidity in the soil. That's related to the seeding process, and so we can do this quite easily. So here's the sensor that was used, was sort of integrated into a version of this was integrated into here, and then it was tracked along, and then it measured the humidity in different soils and in different depths. And you can see here, so this is a little bit the correlation that we got. That was reference against a more established sensor, and you can see the R squared is pretty decent. This is still at prototype stage, and it needs to be miniaturized and probably a little bit made smaller and more robust. But in principle, it works quite nicely. Here is the same sensor for a different application, and this is manure analysis. So especially in Germany and probably in the rest of Europe as well, there's some fairly strict regulations of how much nitrogen, phosphate, and whatever you can have in the groundwater. And therefore the farmers, when they spread the manure, they have to have some sort of control about this. And so the question is, you have to measure a number of parameters, and this is what we've done with this sensor here. This is actually an inline sensor here. This is integrated here into a manure pump. So you have manure flowing through this stuff here, and that gets them pumped into a tank. And the question is, what is the composition of the manure? You can see this here. So here's comparison between an FTIR lab analysis and the sensor, our sensor. If you use NPK solutions are they are synthetical manure sampled, so they are ideal sampled. And you can see under these samples, for all intents and purposes, our sensor measures all these 4 parameters actually pretty well. So here you see an example of how it would look like if the whole thing is integrated into actual manure pump. You can see here the pump was switched on, and here you can now see how the signal sort of increases and in this case, the phosphate was measured, and that actually worked very, very well. We've done then quite long-term testing on these sensors, and this is just a little snippet. So they were installed in line, and you can see, and this is one of the biggest problems with agricultural applications, you need a lot of corrections. Here you can see, just by optimizing the temperature correction that you need, you could see we could reduce the error from something like 13 down to 3 by a factor of 4. Then you have to deal with sedimentation effects, and there are a lot of side effects that you have in agricultural application that you have to incorporate. But the sensor was good enough, and it was now applied to meet there's like a German manure sensor testing certificate that you have to get, and we are considering to apply for that. So the other application here is milk analysis, and here we worked on a project to sort of digitize the milk analysis in Tanzania. This was a bit of a project that had two components. Number one is to measure the actual milk composition and the adulteration. So they are quite creative over there. But at the same time, it's also to develop a software tool so that the farmers can learn, that it becomes a bit of a learning tool, and show them, look, if you do X, Y, and Z, then this is the effect. So, don't do it. So we use this sensor here, and you can see here it's in use. It runs at the moment of a laptop, and the data gets sent to a cloud. And then we've developed our own sort of cloud portal where, depending on the stakeholders, you can get different information. On farmer level, they get the milk quality per day. The center in Tanzania, they have collection centers where the farmers bring their cows, so they get a performance per collection center, and then the dairies can get an overview over all these collection centers. So this is working quite well. At the moment, it's only it's only operating in one area of Tanzania, but the plan is now to extend it to others. A similar project is really, as a previous speaker also mentioned, of the digitizing of in this case, a milk supply chain. And here was the question to, is it possible to integrate a sensor in the back of a milk lorry, so that when the milk gets collected from the farmer, you immediately get milk quality data. It was here in Europe, so adulteration isn't really an issue, but the sooner the dairies know what the quality of the milk is, i.e. what the fat content, what the lactose, what the protein, they can then basically figure out where to unload it and how it should be processed. And so by doing this, you save time and also quite a bit of energy, because at the moment these tanks, they have to wait, and then an analysis is done, and during this time the milk has to be cooled and all this sort of stuff. So the sensor that we have here is not this one, but a different. This has been qualified for military applications, so it has no problem with being installed in harsh environments, and it's also a project that we are looking at. So just to summarize, so we have a nice platform that works on a lot of application. In mid-infrared, you're looking at the fingerprint application, a region of a molecule, so we can detect more or less every molecule within reason. Everything gets manufactured in Germany under an ISO 9001 environment. So, and we are a manufacturing company. We are not a product design company. We really want to manufacture what we come up with. And we are relatively vertically integrated by using different sort of partners that we have close by. And that's really the end of my presentation. And if you have any questions, let me know.
Thank you, Carsten. So we have time for questions. Well, you can prepare for a question. I have one related with the sample cell. Do you think that each application will require in this agri-food industry a specific sampling cell, or with the models you already have, most of them can be covered?
No, most of them can be covered. It just for some application we have issues with a cleaning fluid. So we looked at baked bean production at some point, and they use really aggressive cleaning fluids to clean the pipes and stuff like that. So then obviously you have to use something that's inert against these sort of cleaning fluid. But in general, it's all right. Obviously, you're at the moment mainly looking at liquids or semi-solids at least. Doing solid is a bit tricky in the mid-infrared.
And the applications are still limited, I guess, by also in some applications by the length of the fibers, right?
We don't use fibers.
You don't use fiber at all.
No. Fibers is fibers in mid-infrared is for agriculture. I don't think it's the right way. It's too expensive.
Very good.
Yeah.
I don't know if we have other questions for Carsten. Well, if not, thank you again for your presentation. You see the contact details here in this slide as well. So feel free to let me know if you would want to be introduced to him or contact him directly if you want to discuss some of the projects or needs you have. And we can move to the next speaker. Thank you, Carsten. You can move to Marcel Zevenbergen, program manager at IMEC, and we're going to learn some of the applications in agriculture they have in IMEC. So Marcel, the floor is yours.
Thank you. First of all, can you see my screen? Can everybody hear me?
Everything is fine.
Everything is set. Perfect. So thanks. I'm indeed Marcel Zevenbergen, program manager at One Planet, which is a new research center founded by IMEC and a couple of other partners. So upon that, so One Planet, as I said, is founded by 4 key researchers in their specific domain. So the first of them is IMEC, well known for its semiconductor technology, but also more and more for its photonics technology. And we also work together with Radboud, the Radboud University in Nijmegen in the Netherlands, and the Radboud Medical Center, which is one of the key research institutes in preventive health in the Netherlands. And also the third or the fourth partner here is Wageningen University and Research, which is of course one of the key research institutes in the agri-food domain. So we teamed up and we created this very unique research center that combines both really deep tech knowledge originating from IMEC immediately in close collaboration with domain experts, both from the Wageningen and the Radboud University. So within One Planet, we focus on a couple of research areas. One of them, and that's also the most relevant for this meeting, is the creation of sensors and digital twins for autonomous growing and food processing. I will focus more on the autonomous growing, what is needed there. I also noticed there's quite some interest also in this meeting in inline measurement for food processing. We are looking there, for instance, at waveguide enhanced Raman spectroscopy. If you want to know more, we want to employ that for protein quantity and quality determination. If you want to know more, drop me a message. And on the other hand, we are also creating sensors, digital twins for preventive health and early signaling in the health domain, but this will not be the focus of this presentation. What binds them all together is the need for nanotechnology and also photonics. We see more and more usage in both domains. Now let's put it in perspective. What sort of big challenges do we want to, that we want to tackle with, for instance, with photonics? And one of the major challenges in agri-food is the lack, the less and less availability of labor, and in this case also really expert knowledge. The grower itself has somebody that is overseeing, for instance, a greenhouse. He is aging, becoming less and less available. And for instance, also in the Netherlands, as one of the leading countries in the world, for instance, when Dutch greenhouse builders set up a greenhouse, they also, for instance, fly in a Dutch grower to oversee that. And that is something that is not sustainable anymore in the future. And when you look at this grower, hey, he has lots and lots of already data available. I will not go into that already, but still, based on all this information he has, he still makes decisions on the spot. He knows what to do, how to steer, how to adjust parameters in the greenhouse, for instance. And basically, we call this magical green thumb. This is something that we want to capture. We want to digitize. We already know there will be sensor innovations needed. We have not figured out what exactly, but also in this presentation, I will present you a couple of elements that we're now investigating. Now, down to earth. So what are, for instance, first tasks where we can really help, digitizing, and we call this create digital decision support. And one of them is about pruning. So cutting leaves, cutting, in this case, cutting trees or cutting branches from an orchard tree to create, for instance, to grow fruit. Again, this is a highly expert task. It needs to be done right. You need to cut the right pieces because this will affect the yield and the quality in the upcoming season. It's done once a year with experts that are becoming less and less available. And one of the first steps that we did is we used state-of-the-art LiDAR technology to fully digitize an orchard. And from this whole point cloud, we created a first app, and virtual reality, an environment where you can virtually cut trees. And this is not a game. This is once a branch that really existed in real life. We used all this, all the cloud points to create this representative or representation of the tree. And of course, virtually you can get indefinitely. You can reset it, and basically you can use this to train new pruners. But also, for instance, you can imagine that you use a digital environment to, for instance, train robots on this highly specialized task. So this is our first concept, and already we got the feedback already from experts like this model is not enough. We need more information, especially on, for instance, the color of the leaves, and we want to see even finer details like the buds. So in the next iteration, we will fuse the LiDAR data together, for instance, with hyperspectral or other camera techniques to get the more information that to create this digital assistant. Another aspect that's also important in the whole decision taking is the detection of pests and plagues, for instance, caused by insects. And here we focus on a very particular pest. It's called the Heliamorphis halis, also the brown marmot stinky bug, which is really devastating for orchards, especially in the south of Europe, because A, it's highly camouflaged, so it's difficult to detect, and B, it creates these subskin defects that will not appear visually, therefore also hard to detect with optical or with camera-based technology. So here we focus, for instance, on hyperspectral imaging, where you do have all the information available, so much more bandwidth, optical bandwidth available, and with machine learning we select the appropriate wavelengths that gives the highest discriminative power to detect these bugs still in where they are, and especially when they are well camouflaged and hidden. Another aspect also that has to do with fruit quality, and already in earlier presentations we saw already examples of, for instance, using spectroscopy or other hyperspectral imaging to assess, for instance, sugar content in products. But fruit quality is not only determined by, for instance, the sugar content. There are also other aspects like, for instance, firmness, juiciness, etc. And here we really see where for instance, optical technology is starting to lack. And for some of these very difficult, call it more physical parameters, we see now you need more sensing modalities. And I see this as a big trend also in this field, where you, for instance, fuse different sensing modalities. And in this case, we fused hyperspectral imaging again together with acoustic sensing. And while both sensing modalities give, for instance, a decent correlation with in this case the firmness, when you really fuse that data, you get a much better a much better correlation. We're approaching in this case 96% with the measured firmness, which is done with an destructive measurement, and our approach where we fuse two non-destructive approaches, in this case hyperspectral imaging and acoustic sensing. Now, this gives you a bit of flavor on a couple of examples on where we think photonics can really make a difference in agri-food. I did not touch upon all the technologies that we are focusing on, but this is definitely a growing activity within the research center. It also has to do, the Netherlands is heavily investing into photonics. It is by the means of a Dutch initiative called Photon Delta. And basically, within Wageningen, within One Planet Research, we really want to focus on the linking this new technology. For instance, LiDAR is very much something that is very much driven by the automotive industry. And how can you translate that also these new building blocks towards application in the agri-food? So to conclude, I think One Planet Research Center is a multidisciplinary, really unique collaboration between nanotechnology from IMEC and the domain expertise from the Wageningen University and Radboud University in UMC. We want to tackle these major societal challenges in for instance, the labor shortage, but also the environmental impact, etc. We want to really develop these cutting-edge, high-tech, game-changing innovations, and we do this by combining all these expertises. And also, we work on solutions that in the end are transferable to partners that are collaborating with us. So also, if you see possibilities to work with us, please reach out to me at this email address. Phone number is there. So, and I'm now happy to answer questions.
Thank you very much, Marcel, for the summary of some examples and also the capabilities of IMEC and this One Planet Center. So, time for questions for Marcel. I have one curiosity related with the firmness example you mentioned. Are you thinking in using it as a field application, or is more like a production line or production plant? Well, not production, because you don't make the fruit, but like a plant application. Because how do you install ultrasound technology in the field?
Yeah, that's a good question. So we definitely focus on pre-harvest. So because that's more related to our grander vision. How can we also help steering, for instance, a greenhouse or an orchard autonomously? But also what binds also all this technology together is indeed how we can miniaturize it far enough that it, for instance, can be integrated in for instance, a robot that is scouting, in this case, through an orchard, and that has an arm, for instance, in the first. That arm will be used, for instance, for harvesting, but also while it is then in touch with the product, it can measure all this parameters. It's in close vicinity. It's even touching the fruit, so that binds it. That we also foresee a road towards miniaturization. That it and also had the power requirements for that it can be, for instance, integrated in a robotic arm.
Mm-hmm. Very good. And I have another question related with the pest detection. How difficult is the initial calibration? Because I can imagine that one insect in different plants can produce different. The wavelength can be the same, but at the end, the answer of the camera can be different. So how difficult is this initial process to get real level? Results?
That's a very good question. So still we have not tackled that fully. So we have now also first data sets in a real life environment, especially in this case taken in an orchard in Italy. But also there we are thinking also in various projects, for instance, how to ensure lighting conditions, how to calibrate, for instance, in this case, the camera on spot, etc. So there we are investigating a couple of approaches, but also what you mentioned, that's also one of the like hardest had to go from this initial proof of concept. For instance, you show that it works in controlled condition, and then move towards the real, and also previous speakers noticed that the real life is much harsher than you initially foresee. So you need to bring also your technology to a certain TRL level that you can quickly assess it also in the real life environment.
Yeah, I was thinking in previous spectroscopy experiments that they have in the past, and how difficult it is to calibrate a system to have good results. So having this kind of live situation, I can imagine that it's hard. So good luck for the future work. And Ian from Vortex, you have a question.
Just a general point. I mean, sort of trying to pin down an insect must be really difficult, much more difficult, say, than looking at a stationary piece of fruit on a tree. And when you're able to find the insect, is there a humane way of getting rid of them?
Very good question. Yes, there are some ways also to remove them chemically. Others. Again, this is also innovation. So previously, it was very hard or very much impossible to detect this bug. And so also now for the first time we show that this bug can be detected also in still also in the field. Of course, also the remark of Antonio: is it reproducible? How do you have to recalibrate? For instance, but basically. And this is also why we like also to work with the domain experts. We show, hey, this is possible. That before this it was deemed impossible. But then they start now also. You can ask the follow-up questions. Okay, do we need really to detect individual bugs, or do you just want to give an overall? Hey, the average amount is this and this. What are, for instance, the levels in which you trigger a decision, as you said, to take precautions or measures against the bug, and to be honest, also the experts don't know that yet.
Good, thank you.
Is it possible to mix them up with other bugs?
Sorry, can you repeat?
Sorry, that's not clear. Is it possible that you would get it mixed up with another bug that perhaps you don't want to get rid of?
Yeah. That's Indeed, but that's also something that we do assess. Like what's the quality? Are there false positives or false negatives, etc.
Yeah. Okay. Thank you.
Good. Now we have another question from the Laser Centrum Hanover.
Yeah, hello, this is Merve from Laser Centrum. So we are basically on the other side of insect treatment. So we are treating insects with lasers, so detect them via artificial intelligence and then just zap the herbivorous insects. So is it also possible for you to have a good, give us, for example, good localization data? So we could point a laser to that, because I think hyperspectral imaging sometimes suffers from very bad resolution.
Yeah, good point. Also, so there, this is also a question that we're now tackling. So yes, how to do that? Also there, we're now looking again at fusing. So you get a broader view and then zoom in, for instance, with the hyperspectral camera. Again, something like that we have not sorted out yet.
Okay, thank you.
Thank you for the question, Merv. And Jens Peter, last question for Marcel.
Okay, thank you. I just wanted to comment on the detection of insects, but the last speaker actually was talking about the same topic. So I just want to say that in Norway there is a system that is used underwater to detect lice, small lice on salmon. And it is detected by imaging system and also killed by lasers. So this is actually possible to do even underwater. So just a comment.
Good. Thank you for the comment. And well, you have here in the slide email for Marcel if you want to discuss later on, or let me know if you want to be connected to him so that you can continue. Thank you for this nice presentation and giving some ideas about future projects. And we go to the next speaker. We have Pedram Pat from CSEM. So Pedram, you can perhaps share your screen, and the floor is yours.
Hello everyone, do you see my screen?
Yeah, we see the presentation and we hear you.
Okay, very good. So first of all, I would like to thank EPIC for inviting me and thank the audience for attending. So I'm going to talk about the handheld intelligent multispectral camera produced at the CSEM. It's called the Spectral. And then I will show an application of this camera for food quality control. Yes. First, a little bit about the Spectral. So it's a multi-spectral camera. The spatial resolution is about 1.2 megapixel. It can have up to 15 physical bands. And it's intelligent because we have embedded processing power on it. It's considerable amount of computational power, so it's not only in microcontroller or something like that. So we can deploy serious machine learning or classical signal processing algorithms on that. It's a battery powered, no need for the cables, and also it has a wireless to Wi-Fi connection to connect it to other devices, or to display the output of the processing, or to store the data, or it can be seen also as an edge device for a hierarchical machine learning system in which some part of the processing is being done on the edge and some part is being done on the cloud. So I mentioned the spatial resolution, the hypercube acquisition. It's around 12 hertz. I will explain later that depending on the application, it can be higher or lower. And the 15 physical bands, the bands goes from 400 nanometer to 970 nanometer. This is the processing power that we have on the device, and we can load a TensorRT or TensorFlow codes on that. And we have also a web-based graphical user interface for the user to see the output of the processing, or if it needs to manipulate the data for applications like this. So the one important point about this device is that it's based on active illumination. So I'm not going into all details now, but a few graphs here. We have 15 LEDs inside this device, where you can see the spectrum of these LEDs on the left side. So we can go over all these LEDs one by one. This is one standard way of obtaining a hypercube. But also, since we have full control on the firmware of the illumination system and also processing, what we can do is that we multiplex the LEDs. So we mix the bands. So instead of going over the bands one by one, at each acquisition, we take a mixture of the bands. And if we design this mixture smartly, what we can do is that we unmix them on the software domain. Okay, so this mixing of the bands, it happens on the hardware domain. So once we come up with the optimal mixture, we fix it on the firmware, we set it on the firmware and fix it. And then, for example, with only 5 mixed acquisitions, we can then unmix these acquisitions in the software, and we get, for example, these 14 unmixed bands here. And some of the bands are even nicer than the bands of the LEDs themselves. So this is for a general purpose use of this multispectral device. But again, for each application, we can play with this mixture of the illuminations. For example, in this application, we wanted to classify 3 classes of objects. One was the one type of lentil, the other one was stone and wood. And the stone and wood in this application, they had very similar color to lentils. So like with a standard RGB camera, it was not possible to discriminate between lentil, stone, and wood. So in this application, we optimized the illumination jointly with the algorithm, with the neural network that was going to classify these 3 classes. So this is the important property of this device, that we can optimize not only our neural network or our machine learning pipeline, but also our acquisition part, our image acquisition part. And in this application, with only 2 mixed acquisitions, we could discriminate these 3 classes with very high precision. So here I have a short video of the spectral network. I don't know. Do you see the video actually?
We see that it's moving. Yes.
So here, please notice that here all the processing happens on the device, and the tablet here is just to display the results. So no processing is happening on the tablet. And with only 2 acquisitions, it means that we can, the speed of a hypercube acquisition can go up to 30 hypercube per second. So it's more than video rate. And again, this hypercube is not like a conventional hypercube that has like 2 wavelengths or 2 nicely separated bands. It's a mixture of the wavelengths that is more relevant for this application. And here is the comparison between the performance of a spectral versus the performance of a standard RGB camera. So first of all, whenever we have a multispectral application, we have to somehow compare it with the baseline, which is the RGB camera, to show that having this more complex system of multispectral has some added value for us. So on the left, we have the acquired image of the lentil, wood, and the stone. In the middle, we have the label done by human. And on the right, we can see the classification done by the machine learning algorithm. We see with the RGB image, there's almost no hope to discriminate these three classes. But with the multispectral, we can nicely discriminate between these three materials. And also, please notice that here the processing happens on pixel level. That's why you see this kind of salt and pepper noise, meaning that we don't take into account any shape information to classify the objects. So we per pixel we say if this pixel corresponds to lentil or wood or stone. And with this, I would like to thank you for your attention.
Thank you very much, Pedram. So we have time for questions or comments. I have one perhaps is more a curiosity, but we heard today also about hyperspectral and how hyperspectral is being used. Why do you choose multispectral as a solution?
Okay, because normally hyperspectral imaging is very time consuming. So I'm taking like one hypercube, let's say you need to, it's equivalent, for example, a hypercube with 100 bands, it's equivalent somehow to taking 100 images. So if you have like a moving object or some, or scenes that are moving, then you cannot basically use hyperspectral imaging for that. And the other reason is that the amount of data produced by a hyperspectral camera is just huge. And normally it's much more than what's needed for a specific application. Again, like what I mentioned here, if we use this spectral in a general purpose fashion, then with each acquisition, we get 15 images corresponding to 15 bands. But for each application, we might not need all these 15 bands. Either we might need like 4 or 3 of bands out of these 15, or we might need a mixture of these bands. Okay, so I don't know, 20% of this band plus 50% of that band plus 30% of that band. This is what is optimal for our application. And in this way, we can decrease considerably the amount of data that we acquire, which means that more speed for processing.
So you need a preliminary discussion about the application to, let's say, tune the software to detect the bands that are really interesting for the application itself.
Exactly. So hyperspectral camera for us is more like a lab equipment that we start with to figure out what are the relevant bands for our application. And then after choosing those relevant bands, then we fine-tune our hardware to acquire only those relevant bands, not for the spectrum.
Mm-hmm. Thank you, Pedram. Marc?
Sure.
Yeah, I have a question, so very interesting. But I'd like to ask, how do you compensate for the LED current and temperature? Because, it will change depending on the current, on the temperature, and also the lifetime, what happens after 2 years, no?
Mm-hmm. Yeah, actually, normally the LEDs are quite robust in this sense. but still we can always start with a white reference calibration. So we take an image of a white reference, and so let's say every, I don't know, every 2 years or every some time that we think the spec of the system has changed, we can take an image of a white reference, and then we normalize all acquisitions with this image of the white reference.
But there is no sensor loop into this machine, right? If I understand correctly.
Actually, this white reference calibration is like a feedback. So in the software, we first normalize with this white reference. Okay, so if you update this white reference, then it automatically changes what happens in the processing algorithm.
Okay, thank you.
Sure.
Thank you, Marc, for the question, and thank you, Pedram, for your presentation. And this is a very interesting system. And I think we can move to the next speaker. We have Tristan Athanaze from Piseo. He's going to present the optical design and system performance characterization for agriculture. So Tristan, the floor is yours.
Okay, thank you. Can you see my screen?
Yeah, we see the screen and we hear you.
Okay, perfect. So Piseo is a French company expert in optical and photonics area. So we work for horticulture, but also in other areas of industry.
So, Tristan, we don't see you, so perhaps you can switch on
yes.
again.
Yes, no, you can see me.
Thank you very much.
Okay, perfect. So yes, so Piseo is expert in photonics area. So we are a French company. It's just a problem of delay. Sorry.
Perhaps you can go stop sharing and try again.
Yes.
It happened to me at the beginning as well.
Yes.
So we see the screen again. Yeah.
Okay. So yes, Piseo is a leading platform photonics area. We are in Lyon, small company, 16 people. Okay. So what Piseo is a unique combination of expertise and technical. So that means we have our own laboratory, accredited laboratory, COFRAC and ISO 17025 in photometrics area, in imaging area, and also optical properties of material. I will come back here later. And we also purpose study in consulting and engineering. So that means we are able to make design of optical system. We make a study of feasibility, scouting analysis technology. So everything in a different part of the photonics area. That means imaging or illumination part. We also make a lot of optical risk assessment and prevention. So our laboratory in radiometry, so as I said, is accredited, is ISO 425. We've got a goniophotometers, integrating sphere, luminance camera. So that means we are able to measure every light source in a different way. And in particular in horticulture, we are able to measure directly in PAIR or PPFD, for example. And that's we provide this characterization in our laboratory. We also provide imaging. We also have an imaging laboratory, so we are able to characterize a camera, every type of camera, UV, visible, or infrared. So that means we measure MTF, geometry distortion, SNR, and other parametrical for a camera. And last laboratory at Piseo, we've got a laboratory for material, able to measure reflectance and transmittance for different material, and that allow us to put a result in a simulation software for optical, and able integrate this result to make a bigger study. So as I said, we've got the laboratory and also the engineering part. So for horticulture, we are able to design optical system like a light source. So different light source, so as an example here, but definition of parameter, homogeneity and power. And after expert at Piseo make the choice of LEDs, the operating point. We also make all the design and optical simulation before prototyping, characterization at our laboratory, and industrialization if needed. We also provide this kind of study for an imaging system. So similar to before, we make the definition of the imaging requirements, choose the component and integrate them. We are also able to design special components for special application, UV, visible, and infrared. And all the simulation of the optimization and tolerancing, and also, as before, the mechanical integration and the industrialization of the production. So as I said, Piseo is not a production company, more service company. And yes, to finish, we are also able to provide performance characterization with our laboratory. So we can measure distribution or intensity for the light source in PPFD if necessary, luminous flux in PPF, and the spectral distribution in UV, visible, infrared, and measure the power consumption, system efficiency, and also able to provide the study of a light source to improve performance if needed. So thanks for this and for the introduction of Piseo.
Thank you very much, Tristan. Do you have any question or comment? You mentioned your capability of making some designs. And as you saw in the first slide about the people register, we had some components manufacturer interested in this topic. How do you select the components when you are working with a customer in a design?
Yes, we are able to make a benchmark of different components, so we can choose first on the data sheet, and then we can compare different components at our laboratory. We know most of producer of LEDs, for example, like Seoul before, for example. And yes, we can compare and we choose the best for each application we have to work on.
Very good. And which is the more required measurement for a hyperspectral camera?
We don't have so much for hyperspectral camera, but we have most of requirement for infrared camera, near infrared, at the laboratory.
Okay, near infrared or mid infrared?
Most of are near infrared. We also have some in middle infrared, but most are close to one micron.
Okay, very good. Any other question or comment for Tristan? Well, if not, thank you very much.
Thank you.
Thank you also for sharing also your email address, so anybody.
Yes, you have everything for contact me
afterwards. And we can move to the next speaker. We have Tobias Kreklow, co-founder and CEO of HAIP Solutions. And we are backing hyperspectral imaging in agri-food applications. Thank you for being here today, and the floor is yours.
Yes, thank you, Antonio, for having me here. Do you see the presentation already?
We see you and we hear you.
Perfect, great. Yeah, so let me quickly introduce you to HAIP Solutions. We are a company based in Hanover, building hyperspectral imagery systems, mainly in the environmental industry. The company itself is quite young, so if you haven't heard of us, I guess that's probably the reason for it. So the company is roughly 4 years old, but we are definitely trying to do an impact within the hyperspectral industry with our products. So just let me quickly introduce you to our industries that we are in. So we are mainly trying to serve what we call environmental sector. So that can be agricultural applications, forestry, food industry, in general, environmental monitoring, but also the recycling industry. So we want to try to make an impact with our products that we develop and produce. And yeah, today we want to focus more on the agri-food applications, as it is officially the title of the event today. Actually, here in Hanover, we have one of the biggest agricultural fairs in the world, which is the Agritechnica. Maybe some of you already heard of that. And if you have a walk around and do a tour there, the main buzzwords in the past years have always been, for sure, precision farming. But precision farming only works if we have some sort of sensors to get the information in the end. That's something a lot of people do not really consider in the whole process. And that can be for sure imaging sensors, because then we see something that's maybe not even visible to the human eye. So if we think of these precision farming applications, we definitely have to think also about imaging sensors. And one thing that's always important to consider as well is that we as human beings see just a very small and tiny fraction of the full light that's available. So here a very short basic excursion into electromagnetic radiation, depending on the knowledge that we have in here in the room. So with our hyperspectral cameras, we can definitely see more than just the visible area that we have here highlighted. We can also see into the near infrared or even the short infrared. That's possible to see and detect different things that are not visible to the human eye in the end. What is the base in the end is that every surface or every material has different interaction with light. So that may be absorption, transmission, or reflection. And in the end, that's what typical imaging sensors do measure. So all the remote sensing applications, for example, that we have are mainly the base within these interaction of light of different materials and surfaces. One also very important aspect is, because we already had the discussion here about multispectral and hyperspectral, is that if we consider multispectral sensors, which are definitely cheaper and less expensive than hyperspectral sensors, we also need to discuss about the resolution of certain spectral ranges and also the continuous spectrums that we receive. That's definitely the limitation that we have with some of the multispectral sensors, especially the ones that we see on UAVs, on drones, is that the resolution is actually very, very broad. So to detect very tiny absorption features is definitely not possible there. And that's where hyperspectral comes in. So especially for very high data quality, hyperspectral sensors are probably the better choice, especially in research. So in the end, what we get out of these hyperspectral sensors is not only the typical 2D image, but also, as you see it already here, is the so-called hyperspectral data cube. So we have the X and Y dimension for the spatial view, and then we have a third dimension, which is the spectral bands. So, and then we get these very nice layers of spectral information. And as you can already see, also the spectral signature curves have a quite different look, because in the end we get as I said before, a continuous spectrum in the end, and not only certain points within the wavelength range. If you analyze these hyperspectral data cubes, in the end, you get per pixel a so-called spectral signature. So we can detect what we sometimes refer to as a spectral fingerprint. In this case, we have very typical spectral signature of vegetation, and you can already see there's quite some difference between healthy and diseased vegetation. So the healthy leaves have definitely a different signature than those that are diseased. And that's in the end the base that we use for further analysis, post-processing of the data to check, for example, for certain nutrient deficiencies or also plant diseases. Especially in the vegetation research, there's a whole lot of things that we can measure, which is far out the reach of the human eye. So we humans see the leaf pigment sections. That's also why we see the plant leaves as green, or if they are dried out and stressed, mostly then as yellow or brownish. But there's also some things visible in the near infrared or even the short infrared, which is related to cell structures, but also the water content. We can see the water absorption here, but we can also see cellulose, lignin, protein. All those things do show up in higher wavelength. And one thing that is especially important with for example, the drought that we actually have here in Germany again is moisture content. That's also something that we, as a human eye, we can see the plant is dry when it's totally dried up. But with the hyperspectral imagery, it's definitely possible also to detect different moisture content levels. So to check, for example, which part of a field could get more water, which we should supply first and which should go second. This is something, especially if we're looking towards climate change, which is definitely of high interest, also for the farmers if water supplies are shortaged in the end. Something that is definitely the biggest application, I would say, right now in the agricultural world is the use of hyperspectral sensors for plant disease detection, as this is knowledge which is very, very tough to earn also for human beings. What we see here really is the healthy leaf in the first row, and then a powdery mildew diseased leaf, and you see really the spectral signature changes here. So we have definitely a lot of different reflectances that you can see here. Sure, there's also interaction with the light on the plant leaf. As you see, there's something happening in the second row, and that's something that we can detect in the end. And the biggest challenge right now is actually to see that even before the human eye. This is possible in lab and also on a greenhouse level. But to do this out in the field is definitely, especially to the ambient lighting situation, not too easy. We have 3D structures to map on the 2D imaging system. So there's definitely a lot more things that need to be solved in the future, but this is something we are also trying to work on. And as I already said, the knowledge of detecting plant diseases, for example, is also lost in the agricultural world. So there's not too much knowledge that's being, for example, given in universities doing agricultural studies, and it's sometimes even hard to detect these plant diseases. And as you can see, here we have 3 different examples, which are actually detectable with hyperspectral imaging technology, and you can differentiate between these different plant diseases that are visible here. So why is HAIP solutions in there? It's actually because we want to try to make hyperspectral imagery technology as user-friendly as possible. We saw a big gap when we started in, for example, people trying to connect hyperspectral cameras to drones, to UAVs, but also in other applications, for example, in the handheld world with our black mobile camera, and also in lab-based applications where we see our black box system. We started really with the Blackbird camera, so that's also why I want to go a bit in detail here. What is the interesting thing here? It's a smart hyperspectral line scanner camera actually, but we have 2 modes. One is the hover, one is the so-called line scan mode. So we can actually get 2D images out of this camera without the need of moving the sensor. It's a Visnia sensor, and we have HSI and RGB camera integrated, so you can really use the beneficial high resolution 4K RGB camera next to the hyperspectral imageries, which then gives you quite a good ground truth of what you are actually really seeing, and also see a live stream down to the remote controller. The connection that we have here is a Skyport 2.0 connector from DJI. So it's a connection to DJI Enterprise drones. And DJI is one of the biggest drone manufacturers in the world. A lot of agricultural enterprises have these type of drones, but also in research, it's very established. And the really nice thing is actually that you can connect a whole variety of different payloads to these drone platforms. So it's not only depending on the hyperspectral camera, you can also use LiDAR sensors, you can also use even higher resolution RGB cameras, you can mount whatever you want in the end. And it gives you higher flexibility in choosing the right sensor or payload setup depending on your needs. So that's really a goal here in doing the integration as easy as possible for the end user. If you are familiar with DJI pilots, our hyperspectral camera is exactly the same, as it's completely integrated within the DJI API and environment. One thing I also want to mention is not regarding the agriculture industry, but also more towards the food industry. So we actually recently launched, beginning of this month, the highest available from the spatial resolution short-wave infrared camera, hyperspectral camera that's out in the world. So we have now doubled the spatial resolution. We have a max version available, which is at 1280 pixels spatial resolution, which is definitely a very new thing compared to the 640 pixels that we had in the past. This is mainly a development we did for the recycling and food industry to also keep up with the high frame rates here due to the high conveyor belt speeds. And this resolution actually gives us a lot of possibilities to detect things in the for example, for an object region. So here we have a very typical application regarding food safety. We have rice grains mixed with some sort of plastic particles. You can already see a bit, but if you think of a moving conveyor belt speed, roughly 3 to 5 meters per second, that's definitely very hard to indicate, especially for RGB cameras. And the nice thing about hyperspectral imagery, and especially the shortwave infrared, is that we can really easily classify the foreign objects here to get better food product safety. It's not only the food product safety, but around foreign object detection, but you can also, for example, detect food fraud, but also quality differentiation that's possible, ripeness detection, not only in industrial scale, but also out in the field, something that's very relevant, and to use hyperspectral cameras for that. So it's definitely pre-process, pre-harvest, and also post-harvest, where you can use these type of sensors. That's so far from my side. Thank you for listening and taking the time. If there are any questions, I'm more than happy to answer. And yeah, feel free to have a look on the website to see the current product portfolio that we have available. Thank you.
Thank you very much, Tobias. Any question or comment? I think you saw, Tobias, at the beginning, the presentation from Cesar regarding the blimps as well. Do you think they can be an alternative to drones for some agri applications?
Potentially, yes. It always depends a bit from our side on the sensor integration itself. It's definitely necessary from our perspective to have very user-friendly integration, because otherwise it's a lot of system integration that needs to be done for the end user. And our approach is definitely to make that as easy as possible. In the end, it's just another platform. So it doesn't matter if it's an agricultural robot, a drone, or even this Zeppelin systems. In the end, it's up on the research question that you have or on the application.
Mm-hmm. Very good. Any other question or comment? Well, if not, thank you again, Tobias, for the nice presentation and for showing us all the products, and also this development of the scan solution, because I think it's a very interesting product. And let's move to our final speaker today. Is Marc Juarez from Seoul Semiconductor. He's Innovation Director, and he's going to present the influence of the LED technology in agriculture development. So Marc, the floor is yours.
Thank you very much. So let me share my screen. Here we go. Okay, so thanks a lot. Really interesting, all the presentation that we've seen today, and thanks a lot, EPIC and all the colleagues. So I want to just show you who is Seoul Semiconductor. We are a Korean company. Not many people know about us, but we are the #3 in the world in production of LEDs. So our company is around $1 billion, and we are around 3,000 people, and our aim is to become the #1 in a couple of years. So big challenge for us. Actually, I'm based in Munich, and we are moving Munich and the Milano office. We are closing them and opening a new Frankfurt Innovation Center, where we will have 8 engineers and the headquarters for Europe from July. And then we also have main facilities all around the world. The biggest one is in Vietnam since 2017, and it's really huge. And we are also planning a new one in India to keep supplying the world with lighting solutions, optical solutions, that I will show you a bit on what we do, because the LEDs are really opening many green fields. So that's what we try to supply. So we are the only company that can supply from UVC or deep UV to infrared in mass production. So we don't do a few LEDs. We really do around 2 billion packages per month. So it's really a lot of LEDs what we do for many applications. And we are the #1 in the UV and #3 on the visible lighting. So our main applications: lighting, automotive, displays, infrared, VEXELs, and UV. For horticulture, what we see is lighting and also UV. And maybe from what I've seen today and what I learned, I see some applications for IR and VEX. So I'm happy to learn more about it, because so far in Europe, the demand for IR and VEXEL is quite small and mainly focused for optical telecommunications. So we really look for having the best efficiency, best reliability and lifetime, and really a cost, because as I told you, we try to address the biggest markets. And we can do everything from an LED itself to also a module, an engine, an optics, driver. So we have all of these capabilities in-house, and we supply the main players in the world for horticulture, general lighting, and many other products. Taking the information from my colleagues from Piseo, it's a company I know very well because I lived in Lyon for 2 years and I worked with them before. And I hope we will also do some cooperation more in the future. The horticulture will keep growing, especially indoor and vertical farming. That is a big revolution. Even now, there are some drawbacks that some big companies are collapsing in the vertical farming due to the energy price and many other issues. But I believe will be part of the solution for the food systems and food production in the world. So something to keep an eye on. As you know, the LEDs are already taking all the sodium pressure, high pressure sodium. These orange lights are being replaced with red mainly, but also white. So it depends on the plant, the application, any other parameters. But this is already there. So what is next? No? How we can also improve the LED efficiency, how we can improve the production of the plants. So that's why we also cooperate with many universities and research centers like Wageningen, like in Germany, UM, and Spain, also the cannabis hub in the UPC in Catalonia. So we are also open and looking for more agreements to find the impact of the light in the plants. And also here, for example, I want to show you just a new project that we had with the home appliance manufacturer. They do refrigerators, and now they put also blue light, green light, red lights, UV light, depending on the fruits and what you put inside, so you can keep the freshness of the product. Yes. There are many new applications that with the light we can improve today. As I told you, I show you just a few products that we have also on VEXEL and IR. The applications today are really for illumination, lighting, not really on the spectroscopy or, as we mentioned, the food industry, but happy to learn more about these applications. And if you see something interesting, please contact me and we can discuss about it. And also where we see a big growth market is in the UV area. So we are already well positioned there. And we have UVA, UVB, and UVC. So every wavelength has its own applications, but it's improving rapidly, really fast. So we are improving the efficiency 5–10% every year for most of the products. Yeah? So some examples here is the treatment to strawberries. So we can do a UVB treatment to strawberries and keep their freshness for more than 9 days compared to traditional no treated with light products. This is possible to do for strawberries, for mushrooms, for many other products. So here we can provide you with solutions and studies that we did. Then also very nice example of the UVC for water purification is this municipality reactor. So here we have more than 9,000 modules and the water is flowing there. And there is a sensor in the entry of the water. So what we do first is sensor the water, how polluted it is. And then we apply only the needed energy. So it's not like a UV mercury lamp that is flashing always at 100% power. So here we can use the smartness and the on-off special capability of the LEDs to really improve the energy. Yeah. So this is really interesting. And then we also see new applications that are still in conventional, but I believe in a few months or years will switch to LEDs that are the flashing of the UVC to the plants for powdery mildew, or these applications from a French company flashing the vines, yeah, to also reduce possible issues. So this will be soon done with UVC. So we look for partners to develop new products, to see the new trends, to understand what is the next thing that will happen. And also we look for researchers and companies and research laboratories that are interested to test our latest technology. So this is my presentation and my contact. So if any question, happy to support you and contact with you later on.
Thank you very much, Marc, for presenting your products and also the applications you are covering nowadays. You will have time for questions. Yeah, Pedram.
Oh, thank you very much, Marc, for the very interesting presentation, especially for our application. And maybe I reciprocate the question that you asked me.
Yeah.
So as the lifetime of the LED, so what's the value that you typically give as that?
It depends on several factors, yeah. So it depends which current you put on the LED. It depends also which temperature you put the LED. So the LED can go really high current and high temperature. Then it means you put less LEDs because you extract more light from it, but it's less efficient. Or you can drive it less current and less temperature, and the lifetime will be much better. So we would need to understand what is your main temperature LED, for example, 50 degrees, 60 degrees, and then what is the current on the LED and what kind of LED you use, the mid power, high power. Then at the end, what it counts is the density on the LED, how many amps per square millimeter you have. And from this, we can do the lifetime.
Okay, very good. So maybe I contact you later for these details. Huh?
Please.
And also about the robustness of the bands, not only over time but also within different samples of the
Yes.
LEDs for the same band. So are these data available?
Yeah, with the LEDs, the main issue of the industry is the variability. So we produce wafers, but we don't know what we're gonna find inside. So then it's always we have to select them. So we do these bins, what is called the bins. We have a bin for the flux or the wavelength. We have a bin for the voltage. And at the end, combining these bins, you have your LED. But the variability from one LED to another can be very high. Then when you do devices and you just, let's say you do the parametrics for one LED, at the moment that this LED is not anymore available because the technology advanced or something happened, or there is some change on the binning structure, your model also will have to rechange or recalculate. Yeah.
Very good. So I might contact you later with the email.
Absolutely. We discuss
very
further.
valuable information. Thank you very much.
Thank you.
Thank you, Pedram. Merv from Laser Centrum, Hanover.
Yeah, thank you for this interesting talk. So obviously we are into lasers, but LED technology is of course always very interesting to us, also for first trials and seeing what's economically more interesting. So one question, you said you are working also in the UV range with your LEDs. Do you also happen to have far UV LEDs? So as far as 200 to 230 nanometers? Or are you working on that? Because that's for us, it's a hot topic, light source development.
Right. Yeah, so some years ago, we acquired a company in the US, and they are really the specialist in the R&D for UV. It's called SETI. And SETI, they also do sensors, UV sensors. I can also do the contact. And basically, we already have 222 and 230 nanometer UVC LEDs. The only issue is the efficiency, right? You know, the efficiency for these LED products is very low. So today, a UVC 275 nanometers or 55 nanometers is around 5%, I would say. If we go deeper, maybe talk around 1%. Yeah. So still a lot to develop and a lot to do, but the projection and the roadmaps for this technology is that in a few years, the efficiency will go up and we will be able to to see them more and more in mass production. But it's already done with LEDs in R&D.
Thank you, Merv. Thank you. And Marcel?
Thanks. Actually, I was about to ask the same question. Also, available technology around 220, 225 nanometer, but you just answered it. So thanks.
So do you see a big interest on this technology? It's for the skin penetration, that you can kill all the bacteria without skin penetration mainly, or will you see some other applications?
In our case, it's around nutrient monitoring.
Nutrient monitoring. Okay. Okay. So we can discuss also further of the applications and how do you see the opportunities there.
Yeah.
We are interested to know more. Yeah. Thank you.
Ian from Vortex. You're muted, Ian.
Yeah.
Okay.
Sorry about that. Now, my question is the other way. Did I see on one of your slides you mentioned IR LEDs? And do you do them, and how far into the infrared do you go in terms of wavelength?
Yeah. So I think I'm not really the specialist for the IR because I'm the guy more for lighting and UV. But IR, we do few products. As far as I know, it's around 1050 nanometers and 950 nanometers that are the main ones that we see mainly on the security cameras and all of these products. So we are a company that address the big volumes market. I don't know if this can help you.
Yeah. So are there any plans to go further than 1050?
I believe technologically wise that our company is capable to do it. Then it's always a matter of business case. We are really driven on business case for developing new products.
Yeah.
So if you have some ideas or some opportunities that we can discuss, I can find the answers.
Yeah. Okay. Thank you.
Welcome.
Thank you, Ian. So it's 5 p.m. already, and we have nice questions now with our last speaker. So you can see now the poll. I will like to ask you to fill in the poll so it helps us to define the interest in the topics and to improve for the next time. And I would like to say thank you to everybody for being here. And just as a reminder of these kind of topics, to refresh again that next year we will have in-person events in Norway to talk about agri-food, photonics for agri-food. So again, book the date, April 2024 in Oslo, hosted by DigiFoods. We have a very interesting discussion today with them. So I'm sure that we are going to have a very nice event in Norway. And it's all from my side. Thank you again for being here. Thank you to all our speakers, and see you next time. Have a good afternoon, everybody.
Right. Thank
Bye-bye.
you.
Thank you. Bye-bye.
Thanks.
Thank you.
Thank you. Bye. Bye-bye.
Bye.
Bye.
Bye to everyone.
Thank you. Bye.
Thank you. Bye-bye.